Welcome to part 4 of our lectures on chapter 29. Now we're going to talk about the force on an electric charge moving in a magnetic field. So this is a magnetic field that's external to any current going on. So if we look at a certain number of particles of charge, so we're going to do n particles and they each have a charge q. So if these are electrons, they have that 1.6 times 10 to the minus 19 coulomb charge with a negative sign, of course, but whatever charge they have. So we have n particles of charge passing by a given point in space in a certain amount of time. That's just our definition of current. So we have a certain amount of charge going by a point in a certain amount of time. So if that time is the time it takes for this charge to travel a distance, so let's call that distance L, in a magnetic field, then you can find that distance as your velocity times the time, right? So V is the velocity of the particle. So then we can say that the force on n particles that makes up this current is given by this equation that we've already used. Our force is our current through a certain length in that magnetic field crossed with the magnetic field, but we're just going to substitute in different numbers for what our current is. It's a number of charged particles with a certain amount of charge going by in a certain amount of time at a certain velocity. And we see that the time cancels out. The time doesn't really matter. And so we've got the force on a certain number of n charged particles with charge q moving at velocity v through a magnetic field E, feeling that force given by that cross product equation. Okay, so again, that's just a right-hand rule, right? So we point our fingers of our hand, our right hand, remember, so if you're right-handed, set down your pen, point our fingers in the direction of velocity when they're straight, rotate our wrist around so that our fingers can naturally bend in the direction of our magnetic field, and then our thumb will be pointing in the direction of the resultant force. So the thing we just derived on the previous page was for n number of particles. If we just have one particle, we can divide out that n. So if we have one particle, it's just the charge on that particle times its velocity, and then we're going to take that cross product with our magnetic field B. So the magnitude of the force, since we're using a cross product, has to do with the sign of the angle between the velocity and the magnetic field. So the sign of the angle is maximized when that is at 90 degrees, and it is minimized when that is 0 degrees. So what does that mean? That means if we have a charged particle that's moving in the same direction as the magnetic field lines, that angle is 0 degrees and there is no force felt by the particle. If we have that particle moving at a 90-degree angle from our magnetic field lines, that force is maximized, and it is just the simple product of Q, V, and B. Now you see on this picture to the right-hand side, they are pointing out the difference between a positive charge and a negative charge. So that positive charge and that negative charge, that gives you this sign switch. So you can see the force felt by our positive charge is in the opposite direction as the force felt by our negative charge. This is actually how you can separate out particles and know their charge. You shoot them into a magnetic field and see which way they turn. Okay, so let's do an example using that equation from the previous page. So the magnetic force on a proton. We've got a magnetic field that exerts a certain force towards the west on a proton that's moving vertically upward at a speed of 5 times 10 to the 6 meters per second. So they've drawn that here in figure A. Oops, back up. When moving horizontally in a northerly direction, so we're going to call into the page north, the force on the proton is 0. So they want to know what's the magnitude and direction of the field. So what they've asked for here is B, both the magnitude of B and the direction of B. What they've given you here, we're going to call this first sentence A because it has to do with part A here, or picture A. And this second picture we're going to call B, right? Because it has to do with picture B here. Okay, so a magnetic field exerts a force of 8 times 10 to the minus 14 newtons. So they've given us a force, and they've given us even a direction of that force to the west on a proton moving vertically upward at a speed. So they've given us a velocity because they've given us the direction and the speed, right? So that part A, they have let us know this kind of information, right? We don't know B, we do know V, we do know F. That cross product is going to come into play because we know that the magnitude of F is given by this angle. So one of the things that is cluing us into the direction of the field is actually the second scenario that I labeled part B, right? So when we're moving into the page to the north, this force equals 0. So to the north means that either our angle equals 0 or it equals 180 degrees. So our magnetic field is either pointed to the north or to the south. So for the cross product in situation A, we might go ahead and put our right hand in this situation. So remember your right hand, you're going to point your fingers in the direction of V. That means our thumb's either going to go to the left or the right. So we know that either B is into the page or out of the page, because north and south are into the page or out of the page that have to do with that 0 and 180 degrees. So if I point my hand so that my thumb points in the direction of F, my fingers are going to naturally bend into the page. So we know that north and into the page is our direction of B. So now all we have to figure out is the magnitude. So if north is the direction, and we compare this angle between V and the direction we figured out, this is going to be sine of 90 degrees. This is going to be a 1. So now we've got this simple case where we're going to take, and this is just figured out, we need that second bit of information, that second sentence there to figure out that direction, to know that we can do this. But we're going to say that our magnitude of our force is just Q times V times B. So all we need to do to find out the magnitude of our magnetic field is this simple division, right? And when I do that simple division, I get in the neighborhood of 0.10 Teslas, right? Don't forget our units, right? And our direction is going to be into the page or north, right? So that's how we would logic our way through this using the information from both this second sentence and this first sentence. So without this second little bit, we don't know what we can do with that sine theta if we have to do something other than 1 right there. Okay, so when, oh, and I forgot to mention the one thing that's not perfectly stated, but we've got a proton. Our Q for a proton is, of course, our standard 1.6 times 10 to the minus 19 coulombs. That's what I put into this equation at the bottom. Okay, so moving right along. I mentioned that when we put a charged particle into a magnetic field, it's going to feel a force, and that force is going to be in a direction perpendicular to both the magnetic field and the velocity, right? So force is always perpendicular to the velocity And since force is perpendicular to the velocity, the acceleration is also perpendicular. That just comes from our Newton's second law, right? F equals ma. And if we're going to use vectors, F and a point in the same direction, right? So since the acceleration is perpendicular to the velocity, we can actually use centripetal acceleration here. So we're going back to Physics 1 knowledge and back to knowledge of circular paths. You might want to review it a little if it's feeling a little fuzzy for you. All right, so a negative particle is gonna move clockwise, and a positive particle is going to move counterclockwise, right? That just has to do with the direction of the force. Remember, force for our particles here is QV crossed with B. If Q is a negative sign, that force is going to point in the opposite direction as what your right-hand thumb tells you. Another way to do that is do a left-hand rule with a negative charge. Stick with the right hand and just remember that you've got a negative sign. Okay, so our circular paths example, you're going to submit this one on D2L for your worksheet attendance credit this week. We've got an electron that's traveling at 2 × 10⁷ meters per second in a plane that's perpendicular to a uniform 0.01 Tesla magnetic field. We want to describe its path quantitatively, right? So if we want to describe its path quantitatively, we want to describe what is happening. So what's happening? We've got Newton's second law that says the sum of all forces is going to tell us about our acceleration. Since we are in a plane perpendicular, we know that cross product can just become a simple multiplication, right? So Q times V times B, right? And we know that A is going to have to do with our circular path, so it's going to be a V squared over R. It's going to be centripetal acceleration. So let's set those two things together. We've got Q, V, B. We've got M times A. Right? So quantitatively, its path is going to be a circular path, and its path is going to have a radius that's equal to R equals M times V squared over QVB. So quantitatively, its path is going to have a shape that looks like this. That's dependent on the mass of the particle, the speed of the particle, the charge of the particle, and the strength of the magnetic field that it is moving in. If the magnitude or the speed is constant, we are just going to be changing direction. And if the magnetic field is constant, then R is constant too. So as long as these things are constant, the radius of our path is also constant. So for this particular case, we've got an electron. So I would have to look this up, but an electron has a mass of 9.1 times 10 to the minus 31 kilograms. Remember, kilograms are our standard unit of mass. We are moving at a speed of 2 times 10 to the 7th meters per second. We have a charge, so Q is 1.6 times 10 to the minus 19 coulombs. I'm going to use my absolute value of the charge, because the negative sign here is really just going to tell us that we go in a different direction when we have negative charge, right? So positive charge would go around, like I said, a positive particle would move counterclockwise and a negative particle would move clockwise, right? So in our rotational motion, normally we say that the direction that is counterclockwise is positive. So this is just telling us, yeah, that we're going clockwise. So we've got a certain amount of Teslas of magnetic field. So for this particular particle, the radius of our circular motion is going to be 1.1 times 10 to the minus 2 meters. In other words, it's going to be 1.1 centimeters. So that's how we would use some physics 1 knowledge with this new physics 2 knowledge to describe our circular paths, right? And again, with our physics 1 knowledge, we could describe the period of motion. So period is usually described with a capital T as the time for a particle to complete 1 circular revolution in this uniform magnetic field. So period would be the time to go 1 circle, so 2 pi r is the circumference of this circle, in a certain amount of time. So we would divide it by the speed we're going. Since we already know that we could describe our radius of motion just in terms of the mass, the speed, the charge, and the magnetic field, we can plug that into that period equation above and get the period of motion in terms of those things that we might know. So we might know the mass and the charge and the magnetic field that we are in. What's interesting about this is that you can see the period of motion is not dependent on the speed, right? The speed cancels out there. Then the other thing we can talk about that's related to the period of motion is the frequency of motion. So frequency is just the inverse of the period of revolution. So it's how many revolutions per second are you completing, right? Frequency is always measured in hertz. So a hertz is 1 over a second. So if we're just taking the inverse of period, frequency would just have to do with charge, magnetic field, 2 pi, and the mass of our particle. So again, not dependent on the speed of the particle. Okay, another thing we sometimes see instead of circular motion is what's called a helical path. So helical just means it's a spiral shape. So if we have a velocity that is not perpendicular to our magnetic field, we can split that velocity into 2 components. We can split it into a component that is perpendicular and a component that is parallel. So remember, the force that our particle feels has to do with this cross product. So if we split it into 2 components, the component that's perpendicular, our cross product becomes simple multiplication. And if we split it into the part that's parallel, our cross product becomes 0, right? Because sine of 0, the parallel part, that velocity would be unchanged. So that velocity is unchanged. That's what's causing this helical path. It's a circular thing that is also moving at this parallel speed that is from that parallel component. And the perpendicular velocity is what's causing that circular path. All right, so one place that we definitely see helical paths happening is with the aurora. So in the northern hemisphere, it's the aurora borealis. In the southern hemisphere, it's the aurora australis. So you have charged particles that are ejected from the sun during like a coronal mass ejection that hit Earth's magnetic field, and as the field strengthens towards the poles, these particles spiral in along that magnetic field line, and we see that as them bombarding atmospheric atoms and molecules and causing them to glow, right? So that's what the aurora is. It's charged particles that are spiraled in towards the poles along the magnetic field lines of Earth's magnetic field. Pretty cool application. All right, so next time with our next lecture, I'm going to pick up here with the Lorentz equation, but here is a good stopping point. So we'll take a break and pick up here next time.